Hi guys, welcome to this part 2 of surface area of prisms and cylinders. Now actually the part 1 video was just a recap of measurement. This is very much a surface area of prisms and cylinders. This is the work that is in the Essentials textbook in chapter 6, exercise D. So firstly, what is a prism? Now, when I used to work in a supermarket chain, I had the best idea of a job. That was working in the bakery because they had those fabulous machines that you put the bread in and it shook them up and these razor sharp blades would actually slice the bread. And I thought it was magic. I was like, this is so cool. Who invented this machine? But thankfully, no one put their hands in these things or small children because that would be bad. But wow. Now, I think of a loaf of bread on the whole as a prism. If I can put a shape into my bread cutting machine and it slices it so that every single slice looks identical, it is a prism. Now, again, the orientation is important. All right, I have to be able to see, can I turn my shape around and put it into my bread cutting machine to make every slice the same? So if we look at this top line here, every single one of these shapes is a prism. Why? Because I can put it into my bread making machine or my bread cutting machine, not bread making machine, well, it's not going to make it, into my bread cutting machine, and it will slice them so that I end up with pieces that are identical to each other. That's pretty much to me the definition of a prism. All right. Whereas if you look at the second section here, these are all triangular pyramids, square pyramids, rectangular pyramids. But can I put these shapes into my bread slicing machine in any order or any rotation and come up with the same pieces? No, absolutely not. Pyramids, there's no way I can put a pyramid into a bread slicing machine and end up with equal pieces. It's just not going to happen. I mean, even if I think about it, my base would be that big, my next section would be that big, then that big, then that big, then that big, then that big. Nah, it's not going to work. So we need to be very careful about what this prism business is, because that's what we're going to deal with. Then we look at this idea of surface area. And I think the great thing about maths is that most times, if you understand English, or if you're doing well in English, you'll actually understand better how to do maths. Surface area. Well, let me think. Surface is surface. It's a flat face of something and the area of. Wow! So this can be actually applied to whether it's a prism or not. Here is a quick example. Let's just imagine that this is my cuboid. It can be a box of some description. How many faces does this thing have? How many faces? Now remember, faces is just a flat surface. If we look at this, it's got two, it's got a front, it's got a back, it's got a top, it's got a bottom, and it's got a side, and it has another side. So it has two sides. Each of these are effectively flat shapes. If we look at the front of this, if that was the only thing we could see of the shape, we would probably think it's just a rectangle. And can we find the area of a rectangle? I should go. It's just length times base, or base times height, or base times... What is it? It's base times height. So we know what the base is, and we know what the height is. And so as such, we take those two together and multiply them, and we have the area of the front. Now, again, if we were really, really lucky, the area of the front and the area of the back for a cuboid is going to be the same. So we only need to do one calculation, right? But surface area is just that. Look at each of the surfaces of the shape and find the area. And then total surface area is adding them all together. Lions and tigers and bears, oh my! Those of you who've seen The Wizard of Oz, wow, what an awesome movie. Still to this very, very day. But what am I going to say? Squares and triangles and circles, oh my. It doesn't work the same way and there's way too many syllables and my jaw is now hurting. We're going to look at examples now of finding surface areas of cubes and cuboids. Now, as I said there are lots of ways of actually doing this. I tend to like to draw my cuboids, and I tend to like to think of things as having a front, a back, side 1, side 2, top, and bottom. And because for a cuboid, I can actually pair those two together, I can pair those two together, and I can pair those two together, then if I find the area of the front, then I have the area of the back. If I can find the area of the side, I have the area of that side. And if I can find the area of the top, I have the area of the bottom. Now, lots of other people I know will ask you to draw these things called nets of solids or nets of cuboids. What is a net? A net's a friend of mine. Do you get it? A net. The girl's name, Annette. Moving on, right? Best material. If you imagine eating Rice Krispies or Rice Bubbles or, I don't know, Crunchy Nut Cornflakes or cornflakes, take that box, slice it, and lay it flat so that it's now not three-dimensional, it's two-dimensional, and this is effectively what you'll end up with. So, in this situation, that might be the top, that would have to be the bottom. This would be side 1, that would be side 2, this would be the front, and this would be the back. And again, in each situation now, I would use the information it had given me to find the surface area. I'd use this to find the area of the top, and I know then I'd have the area of the bottom. I'd use this to find the area of side 1. I know I've got area of side 2, and I would look at this to find the area of the back, for example, and I would know I've got the area of the front. Alternatively, when you have a shape that's like this, I actually just color in sections, and I actually say, okay, find the area of that bit, done. Find the area of that bit, done. Find the area of that bit, done. And then you double them and add them all together, and I'll come on to that at the moment. Right, so this is what I'm saying. A cuboid is effectively 6 faces, top and bottom, which are the same, front and back, which are the same, left side and right side, which are also the same. So find the area of the front. I would be doing this. So let's imagine, for example, that this was 6 and this was 10, and we'll say centimeters and centimeters, give it some units. I would then write the area of the front is equal to 6 times 10, which is 60 centimeters, and squared. Don't forget the units, and don't forget it's squared because it's area. And then automatically I would write down the area of the back is also 60 centimeters. Now the reason I'm writing it down is you're looking for the total surface area, which means you want to find the area of the front added to the back, added to the side, added to the side, added to the top, added to the bottom. Well, so long as I just do this one calculation, I might forget that I actually need to double it. I need to think about using it for the front and the back. That's why I always list front, back, top, bottom, side 1 and side 2. Always, without fail. And then, having worked out all of these individual areas, I would add them and add them and add them and add them and add them. And I would write down here my total surface area. There's nothing wrong with using a shortened version, TSA, total surface area. Or if you're in America, there's scary people who stand in the airports telling me that I can't take on a mouthful of water for totally understandable reasons. Moving on to surface areas of cylinders, there is my favorite sweet. My nan, bless her heart, every year buys me about 12 of these cartons of jelly tots. These tubes are fabulous. I can eat all of those in about 6 minutes. I am on a sugar rush for days. It is, I sit in the corner shaking, but wow, what a sweet. Jelly tots, love, 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 love. Those jelly tots are packaged in a cylinder, which is effectively a long circular shape with 2 ends. Now, a cylinder is basically, as I've just said here, 2 circles, 1 at each end, and a rectangle folded around its shortest edge to meet itself. Now, I really wish I was videoing this, guys, because I'd be having a bit of paper and showing you how this all works. But what I need you to realize is, when I actually make the net of the solid, and imagine that this is the circle, here is the front, here is the back, and this here, believe it or not, is the actual cylinder part. It's the bit that curves around here. That's the bit that all the Jelly Tots logo and what have you would be done. Now, this is where life gets exciting. What I need you to realize is, imagine I was to take this and measure all the way around there. Now, as I've said in a previous video, and I'm going to say again, all the way around the edge of a circle is called the circumference. So when I actually take the circumference of that circle, we know it's either pi, 2 times pi times radius, or it's pi times the diameter. And the radius is from the middle to the edge. And I'll do it on this one here, and the diameter is from one side to the other, passing through the origin. Now, if I was to then lay this circumference out flat, I am promising you that actually it will meet and be exactly the same length as that line there. Now, to me, that actually sort of makes sense. Because you're wrapping the cylinder, this curved bit, around 2 circles, if this length here was bigger than the circumference of the circle, it would keep wrapping around each other, and that doesn't make any sense. So To be able to find the surface area, you always have to find the circumference of the circle, because that's going to give you one of the lines here. But what is this length here? How do I find that? Well, if you look at the fact that one circle's at the front and one circle's at the back, then this length here, that depth, is actually this one here. So, how do we now use this to find the total surface area? Right, well, if we remember, we have a circle, and a square, or a rectangle, or a cuboid, or not cuboid, because that's two-dimensional, but we have two circles and a rectangle. And we want the total surface area. So what's the surface area of a circle? Well, the total surface area of a circle, thankfully, is pi r squared. So find the radius, square it, and multiply by pi. But we've got two circles. So again, the total surface area will be equal to pi r squared, which, when I add those together, can be simplified as 2 pi r squared. What do we know about this here and this here? Well, we know that that's the depth, or the height, or whatever it is. So we now know for this one here, the total surface area is going to be given by depth times, now what did we say this long one was here? It was the circumference of the circle. And what do we know the circumference of the circle is? 2 times pi times r. Now the reason I'm going to use 2 times pi times r is because we use r in my area formula. So we may as well use the one with r. Writing out that slightly nicer, it becomes 2 times pi times r. Now, funnily enough, most exam questions don't use d. They use h for height. Yeah. We can talk about this one for an hour, but let's go for h. So 2 pi r h, which, when we add that to my total surface area, gives me the total surface area for a cylinder as 2 pi r squared plus 2 pi r h. I would never remember a formula. I don't like doing that. I always look at it and go, it's a circle and a rectangle, and I'll work them out individually and add them together. So it's totally up to you. There we go, 2 pi r squared plus 2 pi r h, which, for those of you who are well and truly on the road of factorizing, can be written as 2 pi r, and in brackets r plus h. Come back to that some other time. Now, maths is a big fat trick. I say this all the time, and there is a magician about to saw a very, very concerned looking person. Wouldn't be me, I can tell you that. It's going to try and trick you. So prisms can be described as open-ended and closed-ended. It makes a huge difference when working out the surface area. Don't get tricked. Here is a cylinder. If we think about it, if we put every pipe in the ground that was going to carry sewage and electrical cables, all that type of stuff, if every single cylinder was closed at the end, we'd have huge issues with not being able to get pipes through. So, if it's an open-ended cylinder, it means that you only work out the area of the bit that curves around. It means that there are no ends. So open-ended means no ends. Whereas in the situation of my jelly tots, that would have to be closed-ended. Otherwise, you put the jelly tots in, it is going to falleth out. And there is going to be no jelly tots by the time I get them for Christmas, because they'll be strewn all over the floor. So, closed in this situation means there are ends. So, if it was open-ended, we would only have 2 pi r h as my total surface area in this instance. But if it's closed, we would go back to my 2 pi r squared, which is the two circles, plus 2 pi r h. So think about the question. If they give you a question, try and work out, is it going to be open or closed? In many cases, they will actually tell you. Finding the surface area of prisms. All right, so here are some examples showing you how to do this. First things first. My advice to you is split it up into faces. So if we look at this first prism here, what do we have? We have a front, we have a back, we have a bottom, and we have two other faces. So I'm going to call them face 1 and face 2. By that, I mean that this one here is face 1, and the other slanted at the back of the shape is face 2. So, total surface area, split it up. Here we go. Here is the first. I'm going to do this front one first. Area of the front is going to be given by, it's a triangle. So the front is going to be given by 1/2 times base times height. Now don't be tricked. This 7 centimeters has nothing to do with the triangle area. We need to know what the base is. It's 4 because it tells me here, and the height is 6. That's what this is telling me. That vertical arrow is telling me the height of the shape. So what's a half times 4 times 6? 6, 12. So that's going to be 12 centimeters squared. The back, because it's a prism, would have to be exactly the same, 12 centimeters squared. What about the bottom? Well, the bottom, we need to know this distance here and this distance here. Well, we do. It's 12 and 4. So this is going to be 12 times 4, which is 12, 24, 36, and 48 centimeters squared. What about face 1? Well, we need to know this, and we need to know this. Well, as it turns out, that length there is the same as this length there. And if it isn't, I'm just going to say it is. We don't have the context for the question, but I would imagine it would have to be 7 centimeters. It would have to be isosceles. So I now know that face 1 is 12 times 7, and what's 7 12s? That's 84 centimeters squared. And I know that this would also be 12 times 7, which is 84 centimeters squared. How do I now find my total surface area? Well, I would do 12 plus 12 plus 48 plus 84 plus 84, and that gives me the grand total of 240 centimeters squared. Yes, congratulations. Same thing here with this shape. All right, so let's call this example number 2. No difference. I've got a front and I have the back, which are exactly the same. So you need to try and work out what is the area of the front. In this situation, it's a trapezium. So we do a half, adding the parallels, which is 5 plus 8, times by how far apart they are. So 5 plus 8, 8, 9, 10, 11, 12, 13. 13 times 5 sounds big. It's 65, and a half of 65 is 32.5 centimeters squared. That's my front. So the back must be exactly the same. We've got the base. So the base is this distance times this distance. So the base is equal to 8 times 6.3. Wow, the numbers are getting harder. May come back and do that one in a moment, or we may just, because I don't have my calculator here with me today. That's not helpful. So the base is, now we have to be very careful because the base and this top section here are not the same. This one is 5 and this one here is 6.3. So the top in this situation would be 5 times 6.3. We've got the side. We've got this side here that I'm colouring in now, or the back of the shape, or the side. It depends on which way you're doing it. That's going to be giving me 5 high by 6.3 wide. So let's call that the side, which is equal to 5 times 6.3. And finally, this front section here will then give me all of my sides. So what would that be? Well, they tell me that this is 5.8. And they tell me this is 6.3. And then I would, using my calculator, multiply those all together and get the correct answer. Wow, this lesson is already 20 minutes long, so I'm going to have to shift it up a bit. 1, 2, 3, 4. These questions have come directly from the Cambridge Essentials textbook series, and no infringement of copyright has been intended. I just think they're really, really good questions. In this situation, if you're going to find the total surface area, be very careful. Firstly, this one here is a quarter of a circle. That one there is a quarter of a circle. So to find the total surface area of the front, you'd find the total area of a circle, which is pi r squared, and you would then divide it by 4. That would give you the area of the back. The back side here, or the back side, lol. That one there you can find out because you know that that there is 3, and you know the distance back is 10. Likewise, you can find the area of the bottom. Nice and easy for those. The curved side, right? So the curved section. Again, you have to use the idea of a cylinder. What do we know about the area of a cylinder? Well, we know, the surface area of the actual cylinder bit, that's 2 times pi times r times h. That's the whole way around. But how much of it do we have? We only have a quarter. So I would divide that by 4. So that's the way forward of that. Question 2 is exactly the same. But in this situation, we've got 3/4 of the area of the circle on the top and 3/4 of the area on the bottom. So I'd find the area, which was pi r squared for a whole circle, and then I'd multiply that by 3/4. That would give me the area of the top. I would then need to double it to have the area of the bottom. This bit here, this side here, we'd find the area of because it's just a rectangle. This side here, again, we'd find the rectangle. And the curved section, this section around the edge, I'd use the fact that 2 times pi times r times h gives me the whole. So I would then multiply that by 3/4 to get the 3/4. You see what's happening here? Same thing. This one here is a hemisphere, half a circle. So pi r squared divided by 2. That will give you the area of the front, which you could then double to give you the area of the front of the back. This top section here is a rectangle. And I have the fact that it's 2 meters and 1.6 meters. So I could find the area of that just by doing 2 times 1.6. Then we've got the curved bit along the bottom. How do we do that? Well, again, it's that outer section of my cylinder. We know that that's 2 pi RH. So I would work that out and then divide it by 2. And again, same. This is a rectangle, easy to find. The back bit here is a rectangle, easy to find. This curvy bit, not so easy to find. And the area on the front, well, that's a sector. So remember, area of a sector is given by the angle of the sector divided by 360 degrees. Why? Because that's the fraction of the section we've got. And we want to multiply that by the area of a whole section, which is pi r squared. We take that. That would give us the area of the front. We would then multiply that by 2 to give me the area of the back. The bottom bit, right? Again, we've just got a sector. So that bottom section of the cylinder is 2 pi RH. That gives me all the way around the outside of a cylinder. I would then want to multiply that by how much of the circle I've got, which is 40 degrees out of 360 degrees. And adding all those together will give me the total surface area. Again, last shape here. Just be very, very careful with surface area of composite shapes. Here is a composite shape. What do I mean by composite? It's a shape made up of more than one other shape. So I've got a cylinder sitting on top of a cylinder. Now, when you work out the total surface area, you're looking at the area that can be seen. If I was going to paint all of the areas of this, what area would I color in? Now, normally, when you've got a cylinder, you would find the total surface area by using pi r squared 2 pi r squared plus 2 pi RH. Why? 2 circles, top and bottom, plus the curved section. When I then sit that on another cylinder, you're going to notice that there is this section here of area that's never going to be seen. Likewise, the bottom here is never, ever going to be seen. So you have to look at where there is overlap, accounting for that and reducing it, removing it from your calculation. Now, this can be done in lots and lots of different ways. What I tend to do is find the total surface area of this as if it's on its own. I'd find the total surface area of this on its own, which again would be 2 pi r squared plus 2 pi RH. Then I would take away 2 lots of the overlap. And because I know that this is where my shape joins, I know that that would be pi r squared, because that's the area, which I would then double and take it away. So I would do this, I would add it to that, and then I would take away that. You're trying to take away the overlap. And because there is an overlap for both the top shape and the bottom shape, this is why I multiplied it by 2. Okie dokie. That is the end of this section, 25 minutes long. Wow. Well, hopefully it was helpful. I look forward to seeing you next time. It's been so great having you watch this video that I'd like to see you again and again and again. Wow, we could make some amazing maths together. So, if you'd like to, and you'd like to be updated as to when I upload new videos, why not subscribe by clicking the button on the right? Otherwise, if you want to click and see another video created for this type of series, then click the video on the left. All right, well, you have an awesome day, and I look forward to see you again.